Hi everyone. This part of the lecture is about the sampling theorem and some basic baseband modulation schemes that I discussed in today's class. Again, I felt I rushed through this part, so I plan to make a video on it. But just a warning, I won't make videos for everything, only to those places. If I discuss some topic very well in the class, I'll not make a video for it. So you should attend the classes, and there shouldn't be an excuse for you to not attend the classes. So I'll just quickly make that. So for example, I discussed in the class that let's say we have a song which is lasting for say 1 second. I've taken this is a time domain measurement of a song. Okay, someone is singing a song. You took it through to a microphone and amplified it. You got a proper time domain signal out of it. And this is x of t. The problem is now let's say you want to store it digitally. You want to store it. What would we do? Digitally, if you want to store it, this is if you take say this is 1 second, 0 to 1 second, there are infinite number of samples between 0 to 1 because it's a continuous signal. So instead, what we do is we'll compute the Fourier transform of the signal and find the Fourier transform of the signal. Let's say it lies between minus b and plus b. It turns out we know the Fourier transform of the signal and its frequency is always less than minus b and plus b, or most of its energy is contained within this band. Say 99% of its energy is contained. Maybe there may be some energy spilling outside this. It's okay. But if most of its energy is within a certain band, then I can just sample the signal. Okay, this is not a pure sinusoid. I'm just showing it as a sinusoid. I can just sample or take this sinusoidal samples of the sinusoid only at certain intervals. Okay, and this interval Ts should be such that it should be less than or equal to 1 by 2b. So this is called Nyquist criterion. This can be very easily proved. The result can be, I think I'm not doing any proof for this because it's a very trivial proof. You can very easily prove it in SAS, basic SAS concepts using a frequency domain analysis. You can very easily prove to avoid aliasing. We should use this condition. Or said otherwise, I can cite the sampling frequency, the rate at which you are sampling should be greater than or equal to 2b. So this condition is called Nyquist criterion. Okay, if you obey this criterion, just by having these samples, okay, you can completely reconstruct the continuous time signal later on. Okay, just by sampling, you having these samples, it can do that. It's a brilliant theorem. First, anyone when you actually study it for the first time, it should really surprise you. If it doesn't surprise you, probably you haven't understood it. So that's the thing about this. So in fact, Nyquist theorem, we call it Nyquist theorem. In fact, both Shannon and Nyquist realized it simultaneously. So you should all understand this. This was thought of in the around 1940s, 30s and 40s and 50s. So at that time, they were trying to properly put Fourier transforms, Laplace transforms to real world applications. Okay, Fourier and Laplace, they all developed these theories around 1850s, 1830s, 40s. That was the time. All this theory, the mathematics was already there, but to properly put it to engineering, that happened only in 1940s and so. Okay, so Shannon actually wrote this theorem himself, so it's often referred to as Shannon-Nyquist theorem. So but Shannon's name is now omitted, but he is equally contributed to this theory of sampling as well. In fact, Shannon has done a lot more than any other theoretical engineer has ever done. So this is just a small innovation part of his, and so that's why probably it's not even mentioned as in his name is not even credited with sampling theorem. But generally in the past, engineering community used to refer to it as Shannon-Nyquist theorem. It was both, credit was given to both Shannon and Nyquist. Okay, as I said, I'm not doing the proof for it. It's pretty trivial a proof. Any textbook would contain it. You can just very easily show that if you sample a signal in time domain, it's equivalent to periodicity in repeating the signal periodically in frequency domain. So the rate of repetition is going to be Fs. So if you ensure that your Fs is 2b, there won't be any overlapping of the signals. And if there is no overlapping, you can just put a filter here. After sampling, if you just put a filter here, you will get the signal back. So initially what I'm saying is you first began with the signal like this with a bandwidth say minus b and plus b. Let me draw it like this. So or let me choose a different shape. So you began with a signal with a bandwidth minus b and plus b. Then once you sampled it, it's going to introduce periodicity in frequency domain. So you have to repeat the signal periodically in frequency domain like this. So this is your continuous time signal. This is your sampled signal. Okay, I'm showing it as continuous, but it is sampled. Okay, this is the sampled signal. Okay, and uniformly this is called uniform sampling. It's a sampled signal. From this signal, if I want to get back my signal here back, all I need to do is pass it through a filter with a characteristic like this. This is called as a low pass brick wall filter, with say bandwidth minus b and plus b. If I pass this signal through this brick wall filter, I'm going to get a signal like this with a bandwidth minus b to plus b. So I could recover my signal back. This is a very interesting theorem because you just have a finite number of samples. You have lost a lot of information in between. From all this, I just took some finite number of samples and got away with it. So that should be sound a very interesting result, okay, when you first think of it. But yeah, it should really surprise you. But mathematically, it's a very trivial proof to show, and it's a very satisfying proof as well. Okay, yeah. So this was one thing. Now, of course, yes, we can only store finite samples, which is good. But now the amplitude levels again that can also have a continuous variation. Anything that is continuous analog, it can have infinite variations. Okay, so because it's continuous, it's a real number, we again want to round it off to a nearest integer possible. Okay, so first what we will do is we find what is the peak value. So this process, the next step is, the first step is called sampling. So I'm going to discuss what is called as analog to digital conversion. Okay, this is already done in ComSys. I'm just doing this exercise mainly for DNI students. So in analog to digital conversion, the first step is sampling. Once you sample the data, okay, you have discretized in time. So the time discretization is done now. The next step is amplitude discretization. I'm now going to discretize amplitudes. Amplitude is now continuous, was continuous before. I'm going to quantize it or discretize it right now. So what I'm going to do, each sample, I'm going to round it off to its nearest quantizable value. So what do I mean by that is, first what you need to do, you take your signal, analog signal, find its maximum peak to peak value, and then divide that. So let's make this is, I'm just plotting the values, the amplitudes of signal on this x-axis. Let's say this is 0. The signal takes a maximum peak value of plus Vp and minus Vp. Then what you do is, you divide this entire amplitude range into equal regions. This is called uniform quantization, equal regions. And in each region, you are going to quantize it, round it off to some value at its center. Okay, so you can round it off to some value at its center. So I'm sorry, I should. So this entire region, it's going to be rounded off to some value at its center. So let's say this value is 0. This entire region is 0 right now. This can be made as 1. Okay, and this can be made as 2, and so on and so forth. So this you will get a graph like this. Now if you look at it, this axis, the x-axis, is having infinite value variations. But if you see on the y-axis, you can only have finite values. So you can count it of 1, 2, 3, 4, 5, 6, 7, 8, so on. You can count off the finite value. These are finitely, again, this is an infinite to finite mapping. Okay, but the problem here is, in this process, quantization is an irreversible process, whereas sampling is a reversible process. Okay, even though I lose information in sampling, I can recover the lost information completely if I satisfy a certain constraint. If I satisfy this constraint, fs equals greater than 2fb. Secondly, I am also assuming that that's a little bit deeper idea. You are assuming that there is a filter with this characteristic. Right now, let's assume that for academic purposes, I can assume that such a filter exists. Therefore, I can do a perfect reconstruction. There is no error in reconstruction. I could recover my signal in frequency domain back. Again, you should know that if you have a signal x of t, its Fourier transform is a unique transformation. No two signals can have same Fourier transforms. So that's again a fundamental property. So therefore, if I can recover the Fourier transform properly, which means I've recovered my signal also properly back. So this is a very interesting thing to think about. Okay. The second step is amplitude discretization, which is you are quantizing the amplitude levels. Once you quantize amplitude levels, you are fundamentally introducing distortion, because as we discussed in the class, many levels are mapped to a single level, which means once by looking at the output, you cannot say which one was the input. So which means you have lost that information. Okay, fundamentally you can also see this is a nonlinear function. I can model this y equals some kind of f of x. It's a nonlinear function. And you can see it's a non-invertible function because there is a many to one mapping, so it's a non-invertible function. Okay, I can't find x Given y, I can't find what is the value of x. So which is why quantization is an irreversible process. You have lost something from the signal. So there is always a noise or distortion added. So once you quantize amplitudes, you are going to add some distortion to the signal. Now any standard textbook will contain, any textbook, you can just take a ComSys textbook and study the process of quantization. Study uniform sampling and uniform quantization. It's a very simple proof. Once you quantize a signal, you can show that the signal to quantization noise ratio. Signal to quantization noise. So there is a noise here. It's called quantization noise. Okay, anything that is unwanted, there is an error now. You are rounding off your signal to a nearest value, so there is a round off error. That round off error is called quantization error. Okay, that signal to noise and quantization ratio is going to be 6n plus 1.76 decibels. Okay, again, whenever you have gain, signal to noise ratio, we express them in dBs. By now you should know that. So 20 log of signal peak voltage by noise voltage. So I'll call it NP as noise voltage. Okay, or you can also take 10 log of signal power. PS is signal power divided by PN is noise power. So these are the two standard formulae for computing signal to noise ratio. Okay, so this is a fundamental. So when you quantize it, you are going to introduce an error. So then you have to define SQNR. See, if there was no error, SQNR should be infinity dB. Log of infinity should be infinity. Okay, which means there is no noise. NP is 0. If NP is 0, log of 1 by VP by 0 is infinite, log infinity, which is infinity. Okay, it should be as high as possible, but unfortunately, because of quantization, where n here is number of bits, so the number of levels is going to be 2 power n. Okay, again, just think about it. It's a very, very simple thing. I don't want to spend much time on this. It's a very simple thing, the process of quantization. I think some of you, if you have done DSP or any basic course on sampling and quantization, you'd be able to see that. There is a lot of material on the internet. You can study that as well. Okay, so two things. Before you convert a data analog signal to digital signal, there are two steps involved. One is sampling, and the next step is quantization. Now once you quantize it, you are going to convert it into n-bit data. Okay, so this value, when you sample it, this value is called as a sample, and I can say that, let's say you sample it at 1 nanosecond intervals, then I can say you have 1 gigasamples per second. That's your sampling rate. I can also say 1 gigasample. I'm going to get 1 gigasamples in 1 second. 1, 2, if I count the number of samples in 1 second interval, I'm going to get 1 gigasamples. Or I can also say I'm going to get 1 sample in 1 nanosecond, or 1 gigasample in 1 second. So this is gigasamples per second. Okay, the unit here is samples, SPS, samples per second. Now each sample, I'm going to round it off to a certain number of bits. Okay, I have to represent it digitally, so I'm going to quantize it. So that can be, say, it's an n-bit representation. So which means I'm going to compare it to, I'm going to round it off to 1 of 2 power n levels. Using n bits, I can represent 2 power n levels. So I'm going to round it off to the nearest 2 power n levels possible. Okay, so to give an example, let's say the signal takes values from 0 to 1 volt. Okay, I can divide this entire 0 to 1 volt. Let's say, for example, if I take n as 10, so 2 power 10, so the minimum level is going to be 1 by 2 power 10. So anything between 0 to 1 by 2 power 10 can be treated as 0. Anything between 1 by 2 power 10 to 2 by 2 power 10 can be treated as 1 by 2 power 10, and so on. Okay, so this process is called quantization. Now you have so many levels in between. Okay, now 1 gigasamples per second is in terms of samples. In terms of bit, each sample is getting mapped to n bits. So it's going to be n gigabits per second. Okay, when I multiply it by n, because I have to multiply it by the number of bits. So if n is 10, you are going to get 10 Gbps, gigabits per second. Okay, this is the speed with which the data is being sampled. Okay, so in communication systems, in any ComSys, in any communication system, for example, today I'll talk about data. You can actually transmit speech from one point to another point. I'm speaking constantly and you're sampling my speech signal and then transmitting it and receiving it. In any digital communication system, okay, there will be a certain speed with which you can transmit your data. So we probably in the next lecture we'll talk about a very interesting thing called Shannon's capacity, channel capacity. So at that time I'll probably derive it in the class, or we'll see what can be done with that. Okay. So that's a very important quantity. What is the rate at which the data is coming? Okay. So when we were discussing Bluetooth and all those standards, we constantly spoke about Mbps, certain kbps data. So this is what it means. It's sampled, quantized, and then there is a certain rate at which the bits are coming, okay, are being transmitted or received. So that's it for today. I'll probably make a few videos on COMSYS, communication systems, very basics on baseband and passband. We should know the difference between baseband and passband communications. Okay, so this is just a video on sampling. Okay, I felt I don't know how many of you followed it fully. So the intention is just to get you familiarized with these concepts, okay, before we jump into the actual topic.